Okay, so now that we know different components and how different components are laid out in this architecture diagram, let's have a look at sample commands. So I'm going to write a small program. Hopefully it's self-explanatory to you. Try to make sense out of it. Status is equal to busy. Wait. Write data to data register. To command. It's just capitalizing it. Start device. Execute command. Sometimes if I make spelling mistakes, please do pardon me. I'm also speaking and parallel with writing, so hopefully if there is a spelling mistake, you just derive from the word that I spoke or the sentence that I speak. Then again, it needs to wait, so we have a status is equal to busy. What it is doing here is waiting until device is done. Request. Now, this is a program to perform I/O operation on a very simplified device. What the simplified device consists of is let's say this is a beautiful simplified device. Definitely real devices are way more complicated than this, and that's why we call it simplified device. It has resistors, different resistors such as status, data, and command. That's why I wrote those things in capital in the program. And this device has some compute power of itself, some DRAM or SRAM. DRAM or SRAM is dynamic memory, some persistence, that's the disk, or some other hardware. So what we are doing is writing some commands, assuming a very simplistic version of a device, which allows us to do 3 operations. It has 3 registers, status, data, and command. And we want to read or write from the device or to the device. What we would do is definitely first we are waiting here for this device to be free. If this device is busy, then we would keep waiting. So until this device is free. So this waiting is nothing but in the language of storage systems, we call it polling. So we would keep waiting until the device is free. Once the device is free, we would write data to the data register. So whatever the data, let's say the command is to write, then we write that data to the data register. We write the command. Here the command, which is the operation, is to perform the write. All right. And then we start the device and execute the command. So then the device would take that data from the register. It would look into the command, which is the write command. So it would write command with some address of where to write. And then it would take that data, take the command, the write command, and take the address and go into the disk and perform the write. Now, while status is still busy, while device is still doing this, what the CPU does is wait until the device is done with the request, because until the device is busy, we cannot do anything else. Now, this is a very simplistic way in which we could perform any operation. Can anybody see some problems with this? Like, as in the example we discussed, if we want to write 4 KB data to disk, we call this way of writing where we would poll and wait as PIO, programmed IO, where the CPU would issue some command and then it would wait for that device to complete that command before it returns to another task. That's programmed IO. So in such a mechanism, what are the loopholes or what are the problems, or can the performance be improved in some way? And definitely how it can be improved. So first identify the problems, and then we could, once we know the problem, we could think of how to solve that problem. I'll give you a minute to get your thoughts together on what do you think is a problem over here. Well, if you have been thinking that in this piece of code, one of the problem is right written here on the screen, which is polling. And other problem is if the data is too large, then the time it takes to complete this command, or the time it takes to just transfer this data with the word size, because there is fixed amount of data that we would be able to transfer into the data register, because data register is again a fixed capacity or a fixed size. So the time it takes for us to transfer the data from memory to the data register of this device is itself very significant for a large data, because we would have to chop it down into multiple iterations, and that's a time consuming process. So two big problems that we see here is the first problem with program I or polling. The first problem is polling itself, or the time that we waste during polling, right? Because polling is nothing but waiting while the device is still busy. So the time that we waste while waiting, that's the first problem. Then the second problem is PIO for large data size, or the time that we waste in chopping this large data into the size that would fit within this data register's word size, the time that we would waste in multiple iterations of processing this word-sized data before we could even actually begin to write on the disk. That's another problem. So let's look into each one of this problem and then see what we can do now to design a system, a better system that would have resolved the problem or at least improved the problem. The process of how we are discussing concepts in this course also imitates the process of why you think in any research, because this is an advanced level course. So it's just the process of thinking while you are solving any problem at hand. Once you master this process, it allows you, or it helps you to solve any other problem at hand as well. So do observe your process of thoughts and try to catch up with me. Or whenever I say that, let's take this time to think, please don't get distracted. It's not a break. It's not a time to do something else in parallel, check your emails, but it's really the time to think on whatever the question here it is at hand in our discussion.